Um, okay, so you guys all have this one. Let me start from the top. I have a feeder press that's coming to a disconnect, fuse disconnect, as it should, to protect the feeder. From the fuse disconnect, I'm pulling my feeder right into a gutter. This is called gutter, if you can read my handwriting. This is a disconnect switch, a unit NEMA 1 or NEMA 3R disconnect switch, a fuse and a disconnect, number 6. Number 7 is a feeder. Then I grabbed my feeder, actually, as we do inside a gutter, and I tabbed that feeder, tabbed. So I tabbed my feeder, right? Literally spliced into this feeder, and I went down through a fused disconnect, and inside there's a contactor and an overload. So if you put a fused disconnect, a contactor, and an overload, the combo, all this, they call it, guys, magnetic starter, a combination. They call this one a magnetic starter disconnect fuse combination. That box is the green color indicate a box, a physical mechanical size of a box. These are 4 different entities, the green things. So I have a magnetic starter here. Magnetic starter almost always indicate a contactor and an overload. If you make it a combo, actually, they add a fuse and a disconnect to it. And last quarter, guys, we had one here. I think Gary's using it. You've seen it. We put it right here where you have an overcam protection device, a disconnect, and a contactor, and an overload. And out of this system, I'm feeding motor number 2. The same thing, guys. I went here. I have another magnetic starter combo disconnect. Disconnect starter combo. Same thing, disconnect number 2. Number 3 is the fuse. Number 4 is the contactor, the controller. Number 5 is the overload. Number 1 is the branch circuit. I have 2 motors. Cool, everybody can read that, 2 motors. The full load amp for the first one is 520 amps. The second one, 390. The voltage, the horsepower is 200 for the first baby and 150 for the second baby. The voltage is 2.8 for both of them because they're tied to the same system. And we no longer joke with single phase, so we're doing 3-phase. From now on, we're moving 3-phase system. I have a temperature rise for the first one is 40 degrees Celsius, and a service factor for the second one of 1.0. A code letter for the first one is L. Believe it or not, this is an L. Code letter for the second one is an M. Is there anything you want me to read on this screen for you? Anything you want me to read? And we are supposed to size these 7 things based on the information given. Nick, this is typical. You get all this information from the nameplate on each one of these motors. We will be required to provide the 7 things that I highlighted here. And this is not the first time, guys, we touched motors. We touched them in the fall, if you remember. So this is going to be a quick review on these. I have number 8 too. I have 8 is an equivalent grounding conductor. 8 is going to be an equivalent grounding conductor. Okay, let me review what we're going to be doing. Number 1 is the branch circuit conductors. Number 2 is the branch circuit disconnect. Number 3 is going to be the overcurrent protection device for the branch circuit. Number 4 is the controller for the branch circuit, which feeds the motor. Number 5 is the overload for this motor. Number 6 is overcurrent protection device for the whole feeder. And number 7 is the conductor that's going to feed the whole system. And I'm going to size it for both motors. Now, Ashley, if we have 10 other motors here, would it make a difference in terms of how to size 1 through 5? Will be identical. You just keep adding and adding. Where would I use motors? Where would I use this application, guys? I use them with air handling units. I would use them with air handling units. I use them with exhaust fans, pumps, anything that has a motor. What we're going to calculate right now is what you're going to use with every single motor.
What's number 3 again?
Number 3 is going to be the overcurrent protection device for the branch circuit. Branch circuit overcurrent protection device. Okay, any comments, any questions, guys, before we leave that? Any comments, any questions? Comments, questions? 6 is for the system, for the feeder. Now, Ashley, this is what we call it poor woman or poor man's job. When you have a feeder with a gutter and you tap into it, if you want the rich man, we're going to do it later on where we put all these. Chris, we can put all the magnetic starters, the disconnect, and the gutter, all of them in one big fat box, and we call it MCC, Motor Control Center. Remember when we went to Boston Scientific, guys, they were showing us all these MCCs they have in the mechanical room. MCC is a big box that inside the box you have a disconnect and a fuse or a circuit breaker, a contactor, or a VFD, and an overload, all in one big bucket, they call it. We're going to do this later. Any question about what's needed from this system? Example number 1. Any question? Phil, does it make sense? Stuff? Okay. Let's go size them. So what we need to do, guys, is go size them. So what I did for the sizing, I have this nicely, not so nicely drawn thing for you. And since we have 2 motors, most of the stuff is going to apply for both motors, guys. Most of the stuff is going to apply for both motors. So what I did, I drew this one for you. So number one you're looking at is a branch circuit. Number 1 is my branch circuit. That's my number 1. So let me read this one first. We have a branch circuit. Number 2 is a disconnect. Number 3 is the overconduction device for the branch circuit. And we have motor 1 and motor 2. And number 4, what was our number 4? Contactors. And number 5 is the overload. Number 4 is the controller. And number 5 is the overload. Where's the conductor? What was the conductor? The conductor was number 1, I guess. Number 1 is a branch circuit. Okay, any question, guys, about this? Before we go ahead and start doing the calculation. Before I do the calculation, guys, a few things I want to remind you. I kept these for you, so I'm just going to read them for you. We need to go to table 430.250 to get the full load current. And if you go to article 430.22, Chris, it will tell you to size the branch circuit for the motor. The branch circuit for the motor, you need to multiply it by 125. Okay? So let's go ahead, right in here. So to size the branch circuit right here, guys, right in here, I need to multiply the full load current of a motor by 125. Okay, step number 1. Then I would like you guys to, let's just do it one time. I'm going to go just grab my NEC code book and find it just one time, and you guys will get the rest. Let's go to the NEC code book and find the full load current for a motor. So grab this one, and let's go to article 4. Why am I in the 3? 4. Let's go to 430, and we'll do 1, then you guys will grab the rest. So if you go to article 430, we're going to be right in here. Here's a table, Chris, that we're looking at right in here. So if you look at this table, guys, this is table 430.250. I have the first motor, I have 200 horsepower, 208. 200 horsepower, 208. Okay, here's my 200 horsepower. And the voltage, Chad, is what? 208. Okay. A lot of you, if you cross-referencing him, what's the full load current of this motor? 528. Everybody can read that, guys? 208, 200, that will get you 3-phase. The table is 430.250, the full load current, and it's a 3-phase for alternating current. That's exactly what we have, AC system. The question would be, a lot of people, why did I go here, not under this table? The assumption, 99% of the time, guys, you're going to be probably using induction motor. 99% of the time, squirrel cage induction motor. So 99% of the time, going to be in this side of the table, this side. Sometimes we go to synchronous motor. So I want to remind you, this is only for synchronous motor. Unless it says it's synchronous motor, the assumption is what? Induction motor, and we go to the other side. Okay. Any question guys about finding it for 200? Let's go as long as we're on it to the 150. So for 150, Chris, it's right above it, right? Isn't that what 150? Right above it, and that will get me, what was that, 306? 396. 396, thank you. Everybody can see where we got these two numbers from? You're going to go to this table. Why this table? Because we're dealing with three-phase induction motor all the time, almost always. Any question guys about how to use this table? Now on the test, if I give you the voltage of 440, where are you going to go? By the way, you go to the closest voltage. If it's 440, 430. If I give you 480 system, where are you going to go? 460. Everybody knows that? Because that's, if you can see, I don't know if you guys can see that, this is the most confusing part. It says the voltage listed are rated motor voltage. The current listing shall be permitted for a range. Look at that. A range from this voltage to this voltage, from this voltage to this voltage, from this voltage to this voltage, and from this voltage to this voltage. That's why if I'm, for example, if I am at 220 all the way to 240, where am I going to default? 230. If I am between 440 and 480, Ashley, where am I going to default? To 460. Can you guys see where? So if I'm using a European system and my motor is running at 230 or 220 or 240, most of the time our motors in the US we run at 240. So we're going to land right under this column. Any question about this? If you have a Canadian system that runs at 600, where are you going to go if it's running at 600? 575. Can they have a thumbs up, Chad? We got that one. We know how to use this table fully. Cool? That's it. That's the table that you need to use. So let's go take a snapshot of that baby. Now we know how to get that number. And let's go write the number that we got. All right, so let's go back. Was I forward or backward? Here you go. Okay, so now the numbers, we know where we got these numbers from. Right, Chris? So I have my full load current, guys, is 528 amps, and the other one was 396 amps. Okay. Now the code say that if you guys go, if you don't believe Chad, you're going to go to 430.22. It tells you take the full load current from the NEC and multiply it by 1.25 and size the branch circuit based on that. So that's exactly what we're going to be doing. We're going to take a 1.25, we're going to multiply it by 528, and we're going to get 660 amp. We're going to do the same thing here, 1.25, multiply it by 396, and if you, Chris, check our math, will you? 495 amp, okay? Where did I get the 1.25? Where did I get the 1.25? 1.25, that's directly from this 430.22. Done. Okay. So that's the that's the full load current that I need to size based on. Now I need to take this amp and size the branch circuit based on these two amps. Then you're going to go to table 2. Table 3, 10.15, B16. Do you guys remember that? And under which column? Anybody can tell me if it's motors, it's going to go to where? Always default. 75 regardless. If it's a motor, you're going to default to 75 degrees Celsius. So based on these, you're going to go the following. I'm going to go parallel, guys. So let's just do a different color here to parallel. So since it's big boy here, I'm going to go parallel. 660 divided by 2 to parallel. And I came up with a 330 amp. Okay? Then the first one, the second one, I'm going to also parallel. Did I parallel for the second one? Yeah, we parallel for the second one, Chad. And we take 495 divided by 2. Why divide by 2? Because we were paralleling. I decided to parallel. I came up with 248. 248 amps. Did we have any mistakes? Any mistakes, guys? Okay, then the rest is just writing, guys, the sets. So I'm going to have two sets of how many conductors and why? How many conductors and why? Three conductors. Do I need a neutral? No. No neutral with three-phase motors for the most part. So two runs of three conductors. Each one of them is 400 kcm. And what type of an insulation, Chad, do I use? THHN, unless I know otherwise. Same thing here, two sets of how many conductors? This baby here, 250 of three conductors, number 250 kcm. What's the insulation? THHN. Any questions about this? Any question about this? Let me repeat myself. The 1.25 came from 430.22. We got this amp. These are big fat amps. I don't want to pull one conductor, so I decided to parallel. When we parallel at least two sets. Two sets, I can parallel more than that, but two sets is good application. Remember the paralleling we say, when you parallel, stay within 500 kcm or 400 amp. So I'm close to 400 amp, 430. I'm close to below 200, 400 amp here. So I came up with two sets. Everybody knows what a two sets are? Two sets of yes, sir. 330. No, this. Yes. Yeah, this is 330. Just because I'm paralleling. Everybody guys know what I'm doing? I took that because 660 is a big fat boy and I need to parallel. Any question? That's it. Now, tell my friend, if you have 100 motors, you do the same thing for branch circuit calculation. Same thing, no question asked. I can't emphasize with, for motors we default in the table, regardless of the amp, almost always we default to 75. Almost always, regardless of the amp. Almost always with three-phase equipment, guys. If you're dealing with three-phase equipment, almost always we default to 75. Three-phase equipment. The lugs are almost always rated for 75. Okay, any question, guys, before we go? This is the branch circuit conductor. So I have two sets of three conductors, 400 kcm for the first one and 250 for the second one. The second thing I'm gonna size. The second thing I'm gonna size actually, I'm gonna go number 2 and size a disconnect. Everybody knows why we have a disconnect for why do we have a branch circuit for the motor? To feed it, Chad, right? You can't feed the motor without conductors. Why do we have a disconnect for a motor? Why do we have to have a disconnect for motors? Because motors are doing mechanical process, heating, cooling, cutting, and they are maintained by electricians and others, and mechanical and process engineers and the technicians. So when they're going to come and change the oil in this motor, imagine changing the oil and somebody go and the controller gets a message from the laptop to start while somebody's changing the oil in this motor or the bearing in this motor. You're going to kill somebody. So the smarter than Chad decided, after we lost so many fingers inside the mixers and so forth, decided to come up with a physical mechanical isolation of the circuit. So that's physical mechanical knives that you isolate them mechanically, physically, electrically, and you completely de-energize the system, and then you lock it and you tag it like this. When you turn them off, you lock them, you tag them, so you make sure no idiot is going to turn the switch on while your hand is inside the mixer. Okay, so that's based on that one. We have a disconnect. That's where a disconnect is. Okay, here's where I want you guys to go. 430.110, so you can read my handwriting, and DWAL 312 to find the standard. And how do we calculate them though? If you guys go to 430.110, you're going to find the following. It will tell you that you have to take 1.15 multiplied by 528, and that will get me a healthy 607 amp. Same thing, 1.15 multiplied by 396, that will get you a healthy, what's a healthy 455 amps. And then you need to go to DWAL 3-12. Can you guys go to DWAL 3-12? DeWalt. Why do you see it? DeWalt 3-12. Right in the middle of the page, you're going to find the actual sizes of disconnects. That's what we're going to default to. So what's my next standard? From 607, what's the next standard? 607. I can go to 600 or 800. I can go to 600 or I can go to 800. I'm going to go always up. So this one will be an 800 amp. Go up if it's not a standard. And this one would be a 600 amp. Go up if it's not a standard. Now remember, Chris, engineers are allowed to go lower. I can go up like here, 607 for 7 amps. I can go down to 600 amp disconnect, sign off on it as an engineer, and I say, you know what, I can put my neck on the line for 7 amps. And instead of going to the 800 amp. Can everybody get that one? Then they go hire another engineer when it blows up in somebody's face. If it blows up, it might never blow up. And then they say, well, you violated the code, Chad. Here's your license. Take it away from you. Any question, guys? So what's the rule of thumb? The code. What is the code? Go up. Follow the code. There's some judgment here, Chris. Can you see where 607 we went to 800? We could have done for 7 amps down there. But so I always say if it's my project, we err on the side of safety. We go up to meet the code.
Well, that isn't. 800 is less safe than 600.
Yes. No. These are not overcam protection devices. These are not overcam protection devices. These are disconnects.
Just rating the disconnect.
Yes, these are disconnects. You're right. If it was an overcam protection device, these are just so if it's bigger in amps, it can handle more hit. So, okay. Any question, guys, about this? So we have the disconnect. What's number 3? Now that's what you talk about, Chris. The number 3 is the overcam protection device. Everyone, guys, knows where number 3 is. Number 3 is the overcam protection device. Why do we need an overcam protection device, Ashley? Because things will go wrong. There are things that could, over the years, phase A can go to the ground, or phase A can touch phase B or phase C, or all of them touch each other. So you're going to have a short circuit. Line to line, or phase to phase, or 3 phase together, or phase to ground. So the fuse is supposed to get me very high amount of current from a ground fault to short circuit, bam, trips. Okay, so to size these, I need to tell you guys what type of a fuse I want you to use. Because for these, you're going to go to table 430.52. I would like to go to this table in a second. Can you do me a favor? Can you write here dual element time delay fuse? Dual element time delay fuse. I decided commonly use dual element time delay fuse. I'm going to use the dual element time delay fuse, and I'm going to take you guys to the NDC code book, and let's go size a dual element time delay fuse from the table for 430. Here you go. So let's go directly into that table and size one time on once and for all. Go to this table and size, oops, where is it? There you go, Chad. There you go. No. For right here. Okay. Here's the table that we need to go. You guys have been here before. So your friend, Mr. Curdy, you have 4 options, Ashley. Non-time delay fuse, dual element time delay fuse, instantaneous strip, that's the one that's sitting right there in that panel, or inverse time circuit breakers. Commonly used dual element time delay fuse has 2 elements, one overload and one short circuit. Commonly used. Can I use a non-time delay fuse? Yep, you can. Can I use an inverse time? Yep, any one of them you can. Instantaneous strip breakers, these guys are part of manufactured, like MCC, they use a lot of instantaneous strip circuit breakers in combination with an overload. Okay, so we decided, Mr. Kurdi decided to use this one, commonly used, dual element time delay fuse. And we are in a 3-phase system, so we're right here. I don't know if it's going to be squirrel cage design B energy efficient, so I assume it's going to be any 3-phase. And what's my multiplier, Chris? 1.75. 1.75. Any question guys about this? Any question about this? Any question about how to use this table? Everybody knows how to use this table? So your multiplier is going to be 175. If I ask you on the test, guys, to use an instantaneous strip circuit breaker, 800. Time delay, so you can use 800 and you can use 250 or 300. These are your options. Yes, sir. Dual and time delay fuse. And also non-time delay fuse is coming. Manufacturers, guys, make a combo sometimes of an instantaneous strip circuit breakers inside a bucket where they have an instantaneous strip with an overload. So which one is more safe? Dual element time delay fuse. Can you see how they allow you to go very low on that one? Okay, any question about this table? Everybody knows how to use this table, right? Piece of cake. So we'll take a snapshot of that baby. We'll go back to where we were. So we know where the 175 came to be now. Okay, dual time delay fuse. So let's go do the math then. I have 175, right? We said, so that's number 3. I have, did they say 1.75? 1.75 times, I need somebody to do the math for me now. 528 and 1.75 times 396. Anybody can do the math for me? I use a different fuse here. Anyone?
And you multiply it by the full load amps,
Yeah.
not the,
No, you multiply it by the full load amp from the NEC. How much? 915. I need 2 people to agree. 924 to 924. Okay. 924 amp. Okay, what's the next standard based on 240.6? Everybody knows what 240.6. 1,000? Definitely. So the next standard for this baby is 1,000. 1,000 amp. Okay, let's do it for that baby. What's the second one?
796.
Second? 693. 693 amps. What's the next standard? We don't have 650, so we have to go to 700. 700. Okay. 700 amps. A 1,000 amp and 700. Any question guys about these? Okay. Any question about how to size them? I size them. Mine is non-time delay fuse. That's where different level. All right, let's go directly into the controller. Can you guys write yourself a note here? Because my handwriting sucks. So you're gonna write, this is gonna be my controller. Write yourself, we're gonna go size the controller. Number 4 is the controller. If you go to 430.83, it will tell you size the controller based on 2 things, the voltage and the horsepower, okay? And if you go to DeWalt 6-4, it will give you the actual NEMA size. So let's go size the voltage first. So when you size this one, guys, you're gonna see the first, was it 200? You're gonna see it's a 200 horsepower at 208, and this is 150 horsepower at 208, 3-phase. That's the first thing you need to do. The second thing, we need to go to DeWalt and 6-4. Can you guys go to 6-4, please? With me. We have done that before. 6-4. Okay, if you go to 6-4, guys, this will give you an NEMA size. Now we're talking about NEMA. So the voltage that I have is 208. Can you guys see it's 208 right under 200? Am I single phase or three phase, Chad? I'm phase and voltage. So I'm these are all three phase. So we're going to go to a 200 horsepower. What's for 200 horsepower? What's the size NEMA based on 2.8? Do we have one for 2.8? We don't have 2.8. Meaning, what this means, guys, is that 208 you usually, most likely, you don't have to have it. The most common is 480 motors. Okay, so let's use, because we don't have it, it doesn't go all the way. Let's use the one, then we go to the higher voltage. Go to the higher voltage. What's the next higher voltage? 230, 240. So size based on 230, 240. What would that give you? Number 6. Okay, so we're going to go size. That will be NEMA 6 for the first one. And how about the second one? So this is NEMA number 6, and also NEMA number 6. NEMA 6 for both. NEMA 6 for both. NEMA 6 for both. Any question, guys, about sizing it? So we got the NEMAs up and running. Why can't I?
Well, you can't change the voltage of the motor, so it was just a...
I want the higher voltage rating. Not the equipment stays 208, but the contact of the bot is rated for higher voltage than I need, so it's okay.
So it's not a current function,
It's a voltage function. So, for example, if you here you have a panel. The panel can handle 600 volt. Can I tie 208 volt to it? Yeah, no problem. It can handle up to 600 volt, but I can't tie 300 volt system to it.
Oh, because number 6 says it can handle up to 540 amps. So
And that's higher than what we did. Should be.
Really, what you need to look at is the current value.
The current value, the horsepower value, as well as the voltage. From the horsepower and the voltage, you're basically looking at current. You're basically looking at current.
The second column after the name it says 8-hour
Open rating can handle 540 amps. And how many amps do we have for each one of them? We have, for this one, 500 and 400. Okay, so we have 396 here. That's cool. And we have 528. That's cool. So both of them should be able to handle.
That means the voltage goes up, the current's going to go up.
Absolutely. So you need more
You
current.
need to look at the current.
Yeah.
That's what's going to burn.
That's, yes. The current that you in or out. Okay, any question guys about the controller? Based on the horsepower and the voltage, we size an NEMA. Should we go to the overload? Let's go size the overload. Second thing that we need to size is the overload. The overload, guys, I want to remind you, Chris, that for overload, we're going to look at two things. For overload in particular, you need to use the full load amp. Can you guys highlight this one? Full load amp, that's coming from the nameplate. And for overload, Ashley, you have to pay attention to the temperature rise and the service factor. Temperature rise and service factor for overload. These are very, very important things. Okay, so let's go directly into the overload business and just highlight it quick. So for overload, I need to go to 430. Let me just go highlight a few things in 430, guys, and come back right away. 430, did we say? Let's go all the way to 430 and highlight, okay, where am I here, Chad? 430, almost there. Change size and 423, 428, 430, right here. If you guys look at 430, motor overload protection. If you go through the continuous duty, which most of them are continuous duty, and separate overload protection, you're going to go to this table. So please highlight this. That's where you're going to be. From here, Chris, if you say motors with marked service factor of 115 or larger, 125. Motor with a marked temperature rise of 40 or less, don't forget the word less, 125. All other motors, 115. Cool? Everybody's there?
30.32.
430.32 32, what's the 32A1? 32A1. This is 430.32A1. Right, audible? Look at the bottom, I don't want to scroll. Any question how to use this? Can you guys say 115 or larger? Unless you are 115 or larger or less than 40, what's your default? 150. Okay, based on this, let's go look at, oops, only one. Let's go look at our system, guys. So if you look at our system, the first one, I have a temperature rise of 40. Okay, so what's my multiplier for the first one? The second one is service factor of 1. 1, because the service factor is not 115, 1, then I default to 115. Because the temperature rise is 40 or less, it's 40 or less here, right? It says 40. Then I can use 125 for here and 115 for here. Any question why? Because of the temperature here and because of the service factor here. Okay, so let's go ahead and use these multipliers. So the first thing you need to do is for the overload is you need to take 1.25 times, let me use it red here. Now you need to use the nameplate though, 520 amps. You have to use the nameplate, okay? And that will give you 650 amp. And the second one is going to take 1.15 because of the service factor. You're going to use 390 amp, very important, and that will get you a healthy 449 amps. So Ashley, my friend, I can't emphasize to highlight, guys, when you multiply the nameplate, not the code full load current. Why? Anybody knows why? Because overload is the single most important protection for a system. Because most of the problem with this system, guys, is overloading it. The bearing are not working, it gets overloaded. It gets hot, it gets overloaded. So to protect the motor, they want to depend on what the manufacturer are telling you this motor is loading, not what a bunch of engineers and electricians giving you a hypothetical number from point A to point B. Here's the range. So the exact number. This is an exact number from the nameplate, manufacturer driven. So 449. So where do I go from 449? You stop right there. So you're going to come to the overload, guys, right here, and you're going to adjust the overload here. You're going to keep adjusting the overload until you get 650. Now, if you can't have 650, if it's either 640 or 660, you're going to go to 640. You always go down. So what's the standard for it to go up and down? It's what the manufacturers are providing. So for all practical reasons, that's the value that you shall not exceed. You don't exceed. So if my options on the controller is to go for, on this one is 660 or 640, I will go 640. 660 will overload it. Any question, guys, about the overload? So 430.32, and I'm going to add one A1, right? A1. Any question about the overload? Before we move away from the overload. Okay, so we got our overload. We got this, we got this. Now let's go to number 6, guys. Now number 6 talk about the overcurrent protection, and then I'll let you go. Overcurrent protection device for the feeder. Now we're talking about feeders here. That's why we don't have, so we're done with the branch circuits. We have a disconnect, we'll have a fuse, and we have a conductor, and we have a controller, and we have an overload for every one of these motors. Now we're going to group them together, and we need the overcurrent protection device for the feeder and the feeder size. The overcurrent protection device and the feeder size. Okay, You guys can go to the code 430.62, 240. If you go to 430.62, here's what the code tells you for the first one. For the first one, Chris, what was the largest overcome protection device in my system? The largest overcome protection device in my system. The two motors have overcome protection. What was the largest? 1,000, right? So I'll take the 1,000, add it to the full load current of the other motor. What was the other motor? 396, and that will give me easy 1,396 amps. Then take it to 240. If it's not a standard, would you please go down, because they don't allow you to go up. So what are you going to do? Get drunk, get mad, or custom design yourself a fuse, or go down? What's the standard circuit breaker from 240 down? 1,200? Thank you. 1,200 would be my baby. So my overcome protection device right here is 1,200 amp. My overcome protection device right here is 1,200 amp for the feeder. For the feeder. $1,200 amp. That's it. If you don't believe me, Chris, you're gonna go read 430.62, and you're gonna go to 240.6 to find the standard size. Any question, guys? The overcome protection device for the feeder. Everybody knows where number 6 is? The overcome protection device for the feeder.
Why did we take,
The overcome protection device.
we took 1,000 and we went to 396?
Yep, we took the largest fuse in the system,
Okay.
plus the full load current of all the other motors in the system. The largest fuse.
Okay, plus the full.
Why does it? Plus the full load current of everything else in the system. So we took the largest fuse was this fuse was 1,000, plus the full load current of that baby was 396. Then we sized that fuse. We sized that fuse. Any question, guys, about sizing this fuse?
We did one of your examples last week where you had a set of motors, and the method is a little different.
Okay, go ahead, Phil. Give me a second.
Okay, the 1,000 amps is the largest fuse, 396 is the FLA of the other motor, but there was 5 more motors.
Keep adding
Add
them.
those up to that.
Yep, absolutely. Yes, Chris, can you highlight the one? Okay, just check it when you get through. Now, why do we use the largest fuse? Because Nick, if you go to the code, it will tell you use the largest fuse. Okay, so we sized these guys. We sized the largest fuse. Let's go size the feeder that's going to be tapped. When you size the feeder, Nick, my friend, for the feeder, here's what they say. You're going to go to 430.240, and oh, by the way, the table got changed. So the table now, we're going to use, she got married, 310 table, 310.15B16, right? That's a new table that we're using now, the newly named table. 1.25 multiplied by the full load current 528, between brackets, leave them alone, plus, can you see where the largest, fattest, fluffiest motor we multiplied by 1.25? The rest of them 396, you add 396, and if you add all this baby, you end up with 1056 amps. Since they're big, I need to parallel. I want to parallel 6 sets. 105.6, I need to parallel 3 sets. Divide by 3, and I'm going to parallel 3 sets. That will give me 352 amps. 352 amps, okay? I decided, because this is big feeder, I don't want to. So I'm paralleling 3 sets, each one of them. So when you calculate it, then it will be 3 sets of how many conductors? 3 conductors. Each one of these babies are rated for 500 kc an amp. kc an amp, THHM, or equivalent. THHM. Any question, guys? Why did I parallel 3? Because since 3 is giving me close 500, my perfect number to parallel. Any question? Why did they do, you only multiply the largest motor by 1.25. The others are added. Okay, number 8, I added it because of discussion one time happened. Equipment grounding conductor. Now actually, if you're using EMT, you're done. No equipment grounding conductor. But as you tie to the equipment, you need to flex it. When you tie to a machine, you have to put flexible metallic conduit or liquid tied flexible metallic conduit. So you have to run an equipment grounding conductor in the flex or outside the flex, because flex are not rated to provide an equipment grounding conductor. So you have to, with motors, to provide some type of they call it equipment bonding jumper. Equipment bonding jumper. Okay, the first thing about the equipment grounding conductor, the NEC code guys say the equipment grounding conductor does not need to be more than the phases. So no matter what the calculation end up, especially with motors, is a big deal. The equipment grounding conductor must be, or equipment grounding conductor does not need to be larger than the phase conductor. So whatever you end up with, that you don't want to exceed the phase conductors. Not you don't want to exceed, you don't have to exceed the phase conductors. Okay, so let's go and size our equipment grounding conductor. We size the equipment grounding conductor, guys, based on the overcam protection device. For this one, the overcam protection device was 1000 amp, right, Chris? So if you take this one to table 250.122, we're sizing the equipment grounding conductor for motors, for the branch circuits.
Oh,
For each branch circuits. Good point. Now, if we want to size it with the feeder, you're going to go to the 1200 amp. You're absolutely right. If we're doing the feeder, you go to the 1200 amp for the individual ones. So if you guys go to your friend the NEC code book, and I'm going to highlight this once and for all, since you guys are becoming expert in the grounding and bonding system. So we're going to go to Article 420 and grounding and bonding, and 250.122 all the way down, 250.122, 250.66 now closed, 250.122, table 250.122. You guys probably already there. Here you go, 250.122. Now when you go to this table, here's the table that we're going to use. I have a 1000 amp, right? So what's my overcam protection device? 2 watt. Okay? 2 watt. And I also have, what's the other overcam protection device, Chris? 700. And I also have a 700 for the other baby. The 700, they have to go to 800. And what's the overcam protection device for the second one? So it's a 1 watt for the second motor and 2 watt for the first motor. 1 watt and 2 watt. 1 watt and 2 watt. Now, is this larger? Is the 1 watt larger than the 500 kcm? No, so we're good. Is the 1 watt larger than the 350? What was that? We came up with number 2. No, so we're good. So 1 watt, 2 watt. Cool. Everybody get that?
Take care if the EGC is greater than.
They don't. They just say does not need to be. It's just overkilling. Oh, you can.
So it's just a.
Yeah, you just don't need to.
Practical.
Yeah. Safety, no. The bigger, the better. But you reach a point where it's just waste of money. Okay, so let's go back, guys, to this. And then based on 1000, we came up with, what did they say, 2 watt? 2 watts, right? AWG. And this one based on 700 amp, we came up with 1 watt, right? AWG, right? Right here, 1 watt and 2 watt. 1 watt and 2 watt. Any question, guys, about this? Any question about the 1 watt and the 2 watt? Table 250.122, you guys looked at it? Now, here's a question that you're going to ask yourself, Ashley. Is the 2 watt larger than the 500 kcm for the branch circuit? No. then I'm okay. Is the 1 aught larger than the, what sizes we came up with for the 250? So please, can you highlight that one, guys? Everybody understand what this means? Equipment grounding conductor does not need to be larger than the phase conductors. Larger than the phase conductors. Any question, guys? So this is the last time you're going to hear Chad talk about branch circuits and feeders for motors. We move on after that. One example. I know we did a few in the fall of last year. Any question, guys? So that's basically it in terms of. I will give you a homework on that one in a second. Okay. Can we have, guys, 5 minutes break, and then I need to do ACs. Now we're going to go to the AC units. Do the same thing for an AC unit. Cool? Oh, okay. Let's take 5 minutes break. Thank you, guys. A good comment from my friend Chris. He said, why can't we match the overcurrent protection device for feeders, guys? You can match, you can make the feeder, like look at this one. My feeder, my overcurrent protection device for the feeder was 1200 amp, but I sized the conductor for 1056, lower than the overcurrent protection device. That's a permission for motors. You can do that. Can I match the conductor to the overcurrent protection device? Yes, but you will be overkilling. Here's where I match, Chris. Had this 1200 amp been feeding an MCC, a panel, an MCC, a switchgear, no question asked from my mind. If this is 112, if you buy an MCC 1200 amp and you feed all these motors from it, we're going to size this. Definitely, we match the overcurrent protection device. Why? Motor control center. Why? Because if you have an MCC, motor control center, or a panel, you can add to it in the future easily, right? You can add a bucket here, not easily, but you can add to it.
What's the difference between a switchgear and an MCC?
The MCC motor control center has the controller. Let's go back into here to the picture, because pictures is. So if you have an MCC, it will have the disconnect, the overcurrent protection device, and the controller and overload all in one big bucket. Switchgear usually have the disconnect and the fuse. Only these two pieces, switchgear, switchboard. Make sense? Switchgear, switchboard, panel, they usually have these two pieces, which is disconnect the fuse or circuit breaker, but they don't have the controller and the overload. Okay, so let's go, guys, again to another topic, very related, extremely related. Now you're looking at example number 2. And now you can do it as many motors as you want. Oh, by the way, if you want to size, let's go back to our example. If you guys want to, I size the equivalent grounding conductor. I size the equivalent grounding conductor for the branch circuits. What's the size of the equivalent grounding conductor for the feeder? Let's just, I never do that, but let's just add this one as an adder. I'm going to add it here, right here. If you guys can add this one right here. I'm going to call it 8A. And this is equivalent grounding conductor for feeder. I want to run an equivalent grounding conductor for the feeder. So what do? You're going to take the 1200 amp. You're going to take it, the same thing, guys, to table 250.60, 250. Thank you, 122 to 1, 2, and 2. And it doesn't sound as 1, 2, 2. Here we go. Table 250.122. Chris, what is the number? 1200 amp. Anybody has a 1200 amp? Oh, here. For 1200 amp. Right here, so 1200 amp. If I go, guys, to 1200 amp, 1200 amp, 16, 1200 amp is right here. And what's the overcurrent protection device for the feeder then? The equivalent grounding conductor for the feeder? 3 aught. Piece of cake. So for the feeder, I'm going to go directly to the feeder, 3 aught. So what would that give me? How many of them? Oh, how many of them? We didn't say how many of them. How many of these we need? Well, yeah, 3. Why 3? 3 sets. How about here? How many of these 2-aught do I need? How many did I parallel for the first motor? 2, right? I need 2. How many of these do I need for motor number 2? 2. Remember how you're going to have an equipment grounding with every conduit, guys. Right? Everybody knows equipment grounding conductor fully sized with every conduit. That's why we need 2, 1-aught, 1 in every conduit, and we need 3 here because we parallel 3 sets. 3 sets. Cool? Okay, so let's go to a different topic now. Not really different. We're going to go to Article 440. These are HVAC equipment. HVAC equipment. Suppose that you have, this is typically for rooftop units. What we size actually here for rooftop units, for window air conditioning, anything that has a compressor in it. Anything that has a compressor in it. When I say an AC system, guys, you're going to size it based on the compressor. So I have a rooftop unit or an AC system, cooling system 1, cooling system 2. Cooling system 1 has a full load amp of 70, 2 has a 120. LRC, locked rotor current. Now we're talking about locked rotor current. The AC1 has a locked rotor current of 160, and AC2 has a locked rotor current of 450. A locked rotor current, guys, if the rotor that rotates, you literally physically mechanically grab it while the motor is energized, that's how much current you're expected to see out of this motor. That's like inrush. Very inrush, locked rotor current. Okay? The voltage that I'm running these babies at is 240, and they're all 3-phase systems. Any question? Any question? If it's an AC system, Chris, if it's a rooftop unit or an air conditioning, they don't give you horsepower on them. They give you a full load amp. They give you full load amp or rated load amp, they call it. Full load amp or rated load amp. So these are the information that you can get. Full load amp, rated load amps. So I'm going to size the following for this. The number 1 is the branch circuit for the AC unit 1. Number 2, the overcam protection device. Number 3, the disconnect. Number 4, the overcam protection device for the system. 5 is the disconnect. Now I want to size the disconnect for the system. Show you how to size the disconnect for the system. And number 6 is the number 6, my friend. I'm going to size the feeder for the system. Right? Now, some of you will ask me, Chad, what happened to the controller and the overload? Why did I ignore the controller and overload? If you have an HVAC equipment, Nick, 99.9% of the time, the manufacturer will provide the controller and the overload as part of the product. Rooftop units, chillers, and so forth. Very typical in these equipment, the manufacturer will provide them. So we can't get, if you want to size it, it's typical to like motors, but we're not going to go there. So that's what I want to size. Just to spice it up for Chris, because he's my friend, I want to add equipment grounding conductor. I'm going to add equipment grounding conductor, guys, which is right here. I'm going to call this one, where are we here? 7B, and I'm going to call right here 7A, and I'm going to call one from here. How are we going to do that? Equipment grounding conductor right here. I'm going to call this is 7ABC. Okay? I'm sizing an equipment grounding conductor. And by the way, this also will be from here to here, from here to here, and that one, the 7C, will be from here to here. You guys agree with me that there will be an equipment grounding conductor between the gutter and the disconnect? If it's not EMT, but definitely you need them here. If this is an EMT conduit, you don't need them. Okay, any question what the system is? We have rooftop units, chillers, AC units, and we need to size the 5 or the 6, 7 things that we highlighted. Cool? Shall we go start? Everything that you're looking at, guys, is coming from Article 440. That's what we highlighted. We're going to go visit Article 440. We are in Arco 440. Okay, so let's go ahead, guys, and start. The first thing we need to size is, guys, is 440 dot. We need to size the overcome protection, the conductors. We're going to go size the conductors for AC1. To size the conductor for AC1, exactly like any other motor, except actually, we use the full load current from the nameplate. So I want to take 1.25, multiply the nameplate. There is no horsepower for this baby. So 70, and that will get me a healthy 88 amps. The second one, the same thing, 1.25 multiplied by 120, and that will give me a healthy 150 amp. Okay, I need, then you have to go to table 310.15 B16 under 75-degree column. 75-degree column. Okay? If you don't believe me, William, my friend, William is not here. Okay? If you don't believe me where the 1.25 came to be, if you guys go to 240.32, it will tell you, you multiply the rated load amps or the branch circuit selection current by 1.25. Okay. Then based on this, did we make any mistakes, guys? 440.32. Did they say 430? Okay, 440.32. Thank you. That's my milk. Okay, so I need 3 conductors. Each one of them is number 3, and they are A, W, G, T, H, H, N, or equivalent for this baby. The second one here, I need 3 conductors, 1 at each, and A, W, G, T, H, H, N. Any questions? Any comments, guys, about this? Piece of cake. The only difference, Rob, is this 70 came from the nameplate, the rated load amp, not from the code. Why? Because there's no horsepower on the nameplate. They don't come with a horsepower, these babies.
So if you can't parallel number 3.
We're not paralleling though.
3 sets.
3 conductors. Yeah.
3 conductors.
3 conductors because the 3 phase. You're right. You can't parallel number 3. We don't. Yeah, the amp is small here. Yeah. The amp is small. We don't need to parallel. Any question, guys, about this? Now, Rob, my friend, can you write yourself a note here, please? The branch circuit current is called minimum circuit amplicity. Oops, it's writing in this. This is called minimum. Oops. Minimum. Oh, doesn't want a minimum here. Okay, let's write it down here. Minimum circuit amplicity. Can you guys write yourself a note that the amps I calculated, they're called minimum circuit amplicity, and most of the time they're actually calculated by the manufacturer and they put on the nameplate. You don't even have to do the math. Can I get you guys to understand that this 88 and 150 that we calculated based on these rules, the manufacturers stamp, they put them on the nameplate, and they call them MCA, minimum circuit amplicity. If they're there, all what you have to do is just grab them and size the conductor. Grab them and size the conductor. No multiplication needed. If they are not there, then you take the rated load amp, 70, and multiply it by 1.25. Okay? Just write yourself a note, the calculated values, which is this value and this value, it's called minimum circuit amplicity. Minimum circuit amplicity. Cool? Okay, let's go to the overcome protection device, number 2. Now for the overcome protection device, guys, so I have my overcome protection device. For overcome protection device, I'm going to take you to the article. Let's go directly to the article, and let's go to 440. Let's go to 440, and we need to go to 440 dot, in my case here, we're going to go to 440.22, 44, Article 440.22, 411, 14, 22, right here, 440.22, with or without addition. Oh, Chad, 440.21, 22, right here. Okay. I want you guys to highlight this one. This is where you size the overcome protection device for the motor. If you read this, it says individual motor compressor. That's the HVAC equipment. So long story short, you have two numbers. You have 175 and 225. 175 and 225. Read through it. It will say you take the rated load amps, multiply it by 175. And they didn't tell you to go up or down, so you have to go down. And if the motor, if you continue reading it, it says if the motor does not start, if you know your motor doesn't start, then they allow you to go use up to 225. So what are the rules? Rule number one is you start with this value. If this value doesn't give us, and every time we start the HVAC equipment trips, then we go to 225. Cool? So I'm going to start with 175, size based on 175. Cool? Everybody can see that? Right? Where 175 is going to come to be, and there is no going up. The maximum says the maximum, not to exceed. Everybody can see where it says not the sitting, blah, 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 not to exceed. Not to exceed. Cool? So if you guys went there, you're cool. So we got that baby. Got it up and running. So I need somebody to help me because I sized it differently in the past. So we're going to take 175. Where am I check here? So I'm going to take 1.75 times 70. I need somebody to give me the answer, please. 1.75 times 120. What's 1.75 times 70?
This is times the full load.
Yeah, all of them are the full load amps here. How much? 133. Second? Second? 123? 123 amps. Now if you go to 240 and you have to go down this time, you can't go up. So what's the next standard down from 123? 110? There's 125, 110, and so it's going to be 110. Can you guys check on that? 110 amp. Is it 115? I can't. I think it's 110, the next standard. 110. Okay. The second one, 175 times 120. 210. Second. Okay. 210. 210. Thank you. Oops, not 270, Chad. 210. 210 amp. If you take it to 240.6, what's your next standard? You're going to go down to 200. Thank you. 200 amp. Thank you. 200. Okay, 200 and 110. Piece of cake. Now, if you put the 200 and doesn't start, then they allow you to go change it to 1.25 times that full load current. But there's that will be misery. Why? Because what if that size doesn't fit in your panel? And by the way, guys, it could happen that the size doesn't fit in the panel. You have to change the whole panel. It's easy if that circuit breaker can fit in the already existing panel. If it doesn't fit, then you have to change the panel. That's pain in the butt to change the panel. Okay.
Well, maybe you should know what it is before you order the panel.
That's exactly what they do. So manufacturers, because of this, the manufacturers, guys, tell you one little thing I want you guys to write down, please, here. Maximum overcurrent protection device. Maximum overcurrent protection device. So the manufacturer come up with, because of this, they come up with something called maximum overcurrent protection. Maximum overcurrent protection device. So this will be the maximum overcurrent protection device. So what they do on the nameplate, Nick, they go and they put 110 amp fuse or 200 amp circuit breaker from the get-go. So now I don't have the nameplate yet, Chad. So when we do this for the rooftop units, when we size them, we go to the mechanical engineers who are sitting most of the time in the same building. So you guys are sizing rooftop units. Can you give me a cut sheet about the rooftop units that you have to pick? And they have to. So they give you a cut sheet. In the mechanical schedule that you guys have done with me last quarter, and you're going to do it this quarter, you pick the overcam protection device based on the manufacturer specification on the cut sheets that you got from the mechanical. So you go there onto that cut sheet, it will say MO, maximum overcam protection device, 110, and it will tell you it's a fuse, you stick with a fuse. Circuit breaker, you have to stick with a circuit breaker. So because of exactly what you said, because I don't know, is it 175 or 225? So they write these exactly like the minimum circuit ampacity guys, right here. These two values will be on the nameplate. Can you guys give me a thumbs up that, yep, we understand, Chad? If we are to size rooftop units, we need to whisper in the ear of the mechanical engineer and get the information. Okay? And get this information from the mechanical engineers. If you don't have this, you still have to have some information about the unit so you can size it yourself. Okay, cool? Because of exactly this situation. Okay, the second two things, guys, are interesting because of two different things. Now we need to size the disconnect. I need to size the disconnect. Any question, guys, about sizing the conductors and the overcam protection device? And everybody knows that these two are on the nameplate, so I really don't need to size them anyway. If I can get this information from the vendor or from the mechanical engineers. Okay, let's go to the amp rating disconnect. The disconnect, guys, disconnects, this time, I'm gonna size the disconnect differently, and I'm gonna go slightly differently, not a whole lot differently. 240.12, I think. 240.12. 1112 rating of a disconnect and capacity, amp rating. Okay, I want you guys to go right into here. 440. 440.12. What did they say, Chris? I think it's 2 is the lucky number today. Disconnect. This will get you 440.12 rating and interruption of the disconnect. Okay. Two things I want you guys to look at. Number one, the amp rating. What's the amp rating, Alaribo? You multiply, what's the multiplier? I highlighted it, 125%. Amp rating, you multiply by 125%. 115%. 115%. Did I get my mouth today? 115%. Multiplied by the nameplate rating. Cool? 115% multiplied by the nameplate rating. The second thing that you need to do is the equivalent horsepower. Can you guys highlight this one? You need to find the equivalent horsepower. The equivalent horsepower. In the equivalent horsepower, if you read through it, guys, you need to size the equivalent horsepower based on the nameplate. You're going to use table 250, 430.250, and also you need to be able, the horsepower rating from 250.50. I want to highlight this one, and also I'm going to highlight the other one. 2 things. There are two, when we size disconnects, there are 2 calculations you have to do. 2 calculations you have to do. Number one is the amp calculation, 115 times the full load current. That's the amp calculation. Number 2, the horsepower calculation. The horsepower calculation, I'll show you. What I want you now is to highlight equivalent horsepower. You have to go to 2 tables, 430.250 and 430.251b. Okay, so this is the amp. We size it with amp size, and this is these 2. You have horsepower size. Okay, from these 2, we use both of them, and we pick the one that gives us the largest. Can you guys highlight this for me, please? Because that's new. I've not done that one before. Cool. Let's go do it. So let's go take a snapshot of that baby and go directly into into all right. Okay, so let's go to the amp rating. Let's go size this baby based on the amp rating. The first amp rating we're going to do, Chris, is 1.15 multiplied by 70, and that will give us 81 amps. And based on DeWalt 312, what's the size? 100 amp. Piece of cake, 100 amp. The second one, the same thing, guys. 1.15 times 120. That will get you a healthy 138 amps. And the next standard is 200, right? 200 amps. Any question, guys, about sizing it based on 115? Piece of cake, exactly like we did for motors. 312. Right? 312, like we did for motors. Okay, cool. Piece of cake. Now, sizing the horsepower is kind of a tricky. For the horsepower, we have to size based on two things: the full load amp and the locked rotor current. The full load amp and the locked rotor current. So I call it horsepower A, horsepower B, and we choose the largest. Okay, let's go size based on full load amp. So based on the full load amp, Chris, full load current was 70, right? 70. You're going to go to 430.250. Let's go there, and let's do the other one as well as with it. And full load amp here, 120. Okay, let's go size based on the full load amp from the NEC code book. 250. Okay, so let's go to 250. Where were we here, Chad? If you go all the way back, 250 is not far away from here. There you go, 250. All right, so what was the voltage? Everybody remember what the voltage was? 240. The voltage was 240. So here's how you do that. You need a horsepower. So I want to remind you guys, the full load amp for the first one, we are in 250. We are under voltage of 230 based on this criteria, right? Everybody knows. And we're trying to find the horsepower rating for the disconnect. Okay? Based on this, I don't have a horsepower. I need to find a horsepower. So what was the amp? 70? The amp, after we multiplied it, so we're going to, after we multiply it, the amp, after we multiply, okay, no, we need the amp itself, 70. So let's go all the way under here, 70, 70, 70. I don't have 70, so I have 80. So 80 is equivalent to what horsepower? 30. Okay, so we got 30. All right, so let's do the second one, 120. The second one is 120. I don't have 120, I have 130. And this will be equivalent to a horsepower of what? 50. A horsepower of 50. Cool? Any question, guys, about how to use this table? Any question about how to use to find the horsepower, equivalent horsepower for a full load amp with an HVAC equipment? Okay, so what's the size, Chad? The size is 30 for the first one and 50 for the second one. Let's take a snapshot at this and go back into our calculation. All right, so everybody knows where we get from this table 430.250. We came up with 30 horsepower here, right, guys? We came up with 30 horsepower and 50 horsepower. Everybody knows where the 50 and 30 came to be. Cool? Piece of cake. The second one is tricky. The second calculation is B is based on locked rotor current. Locked rotor current. You guys remember the locked rotor current was given? The locked rotor current, bam, 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 bam. Oops, no Chad here. Don't go wild here. Okay, there you go. Can you guys see the locked rotor current right here given? The locked rotor current is given on the nameplate 160 and 451. Okay, everybody can see that 160 and 451. All right, so let's go back into locked rotor current. The first locked rotor current is 160. 160 amp. The second lock rotor current is 451 amp. Both of them are lock rotor current. I need to go to 430.251B. Now I'm going to a different table to size the horsepower rating. I do horsepower based on two calculations. I did the first one, came up with one calculation, second one, another calculation, and I choose the largest. So do me a favor. I'm going to go to this table in NDC code book. This table, guys, is right here, not far away from the first table that we were in. Oops. Right in here, B. Right? Okay. I don't know. We haven't been in this one. Okay, so let's go work on this table. The first locked rotor current, Chris, was 160. So you're going to go first. You need to go to 430.251B. Why B? Because it's three-phase. And the voltage that we're looking at right here is this, right? Because my voltage is 240, so I have to stick with this. For design B, C, and D, all the induction motors are here. Okay, so the locked rotor current, the first locked rotor current, 160. So I'm going to go all the way to 161. Can you guys see that? And drop that baby all the way. What's my size? 10 horsepower. Oops. That's a bummer, huh? Let's go to the second one. The second locked rotor current is 451. Continue. 451. I don't have 451. I have to go all the way to 580. Slam that baby all the way. What's your second size? 40. So based on the locked rotor current, guys, the disconnect that you look here, here's what they want. When you size a disconnect like this, they want you to be able, they want the disconnect to be able to disconnect the full load amps as well as the air rush. Because if it's not rated, that's what we're sizing based on air rush. If it's not rated to start, like the motor is ready to start here, and you're not supposed to do that, but you want to turn it on from the disconnect. Now this disconnect is going to be a huge amount of current going right through it. If it's not rated for this, it could explode. That's what they're sizing based. Now the motor is up and running, right? And you're not supposed to do that. You're supposed to push the button to stop the motor. So say Chris went while the motor is running, disconnect, interrupt the motor, basically de-energize it. Now you are interrupting the full load current, right? Because the motor was running. They also wanted to be able to interrupt the full load current safely. You're not supposed to do that, but if somebody do it, it's not going to explode. That's what they're sizing these two values. And you choose the largest. Okay, so everybody knows how to use this table. Any question about this table? Based on the voltage, and you reference it. Okay, so the sizes that we came up with is 10 and 40, right? So close that one. Let's go back to 10 and 40. So there you go, Chad. I came up with 10 here, horsepower, and 40 horsepower. Now, can you guys now, who's going to tell me which one am I going to use? My option here, it gives me 50-40. Which one are you going to use to size? The largest. 30-10. Which one are you going to use? The largest. So what's the size of this disconnect? This size of the disconnect, 100 amp, 30 horsepower. A size of the second disconnect, 200 amp, 50 horsepower. Any question about that? We find 2 horsepowers and we choose the one that gives us the largest number. Any question? Why? Because the first one will be able to interrupt the full load current. The second one will be able to interrupt the locked rotor current. So if 30, the higher the horsepower, guys, the better the disconnect means. It can handle up to 30 horsepower, up to 50 horsepower. But what's the drawback, Ashley? Cash. Horsepower rating, more expensive. They make them thicker. Yes, sir. No, the full load, the locked rotor current usually is 6 to 8 times more than the full load current. But we use different tables though. See where we went to different tables here? That's why in this case, the full load current gave us more than the locked rotor current because we use different tables.
Now how do we discern between the difference between 100 amp and the 30 horsepower?
They will be on the nameplate. It will say 100 amp, 30 horsepower, right? Stabbed on the nameplate. So they rate them with a horsepower and an amp. Yeah. Or it could see.
Big R station, yeah, 4 or 100 amp or 30 horsepower or 10 horsepower. We dropped the 10, we got the 30.
So
We
my,
have 100 or 30 horsepower.
no, and,
Yeah,
these are and.
right.
100 amp and 30 horsepower rated motor versus 100 amp and 10 horsepower rated.
Okay.
The 100 amp stays there. It's just which horsepower you need it to rate it for.
Okay. The disconnects don't have horsepower.
The disc, not here. The disconnects, yeah. The ones that we chose here, the one that from the DeWalt 3-12 guys, we just size the amps. So when you order your machine now, you're going to write on the machine, on the disconnect, you're going to say 100 amp, 30 horsepower rated, NEMA 3 or NEMA 1 disconnect switch, 3-phase, 480. Yep. Any comments? Any questions? Okay, so that's basically the disconnect. Let's go to the feeder. Let's go, guys, to the feeder. Okay, feeder overcam protection device. Feeder overcam protection device, Chris. If you go to Article, and I want somebody to verify this one. If you guys go to Article 440.22b1, it will tell you the following. You need to pick the largest overcurrent protection device in your system. The largest overcurrent protection device in your system. What was the largest? 440.22b1. The largest overcurrent protection device is 200 amp. Plus the full load current of the other 70 equal, that will give you 270 amps, and go down if it's not like motors, you go down if it's not standard. What's the down from 270? 250, Chris? There's no 270, there's 275, no, we can't go to 250, right? So my overcurrent protection device is 250 amps for the feeder. Any question, guys, about this? Any question? 200, 270, it goes down to 250 amp. 250 amp. 250 amp. Any question? That's like motors, typical like motors, the largest overcurrent protection device. If you guys write yourself a note here, this is the largest overcurrent protection device. The largest overcurrent protection device. The largest overcurrent protection device. Any question? Okay, the second size, guys, is disconnect size for feeder. Now, Chris, my friend, let's go back all the way to here. All right, now, typically we only have one disconnect per machine. That's the perfect situation. One disconnect per machine. A disconnect the machine. If you have a process, guys, the two disconnects is either or, not together. You don't have to do them together. I size a disconnect for each one of the machines. Now, if I decided to have one disconnect for the two machines together, the only place you can do that if the two equipments are in the same machine. So say if you have two HVAC equipment in one big fat air handling unit, and you need to disconnect them simultaneously together. Okay, they're all in one machine, or functionally associated, like in a process control. You can have one disconnect that disconnect multiple motors. Again, I can't emphasize, the rule is a machine, a disconnect. That's the typical rule. The exception is one disconnect multiple machines if they're functionally associated, doing the same thing in the same enclosure. Okay, so now that's what we're sizing. Number 5. Everybody can see where we're sizing number 5. Do you guys agree that number 5 is going to see the full load amp of both of these babies? Right? That's a main. Okay, so let's go and size number 5. Here's how we size number 5. If you guys go to the amp, you're going to go to 440.12b and DeWalt. If you guys go to 440.12b, it will tell you the following. You need to take the following. You need take 120 plus the largest motor plus 70. Both of them, multiply them by 1.15. can I get you to understand that you add them up and then you multiply them by 115? You add them up. A lot of people get confused here. You add them up and then you multiply them by 115. Okay, no problem, Chad. Equal, so you add them up, you end up with 219 amp. Now take this one to DeWalt, 3-12. What's the next standard from 219? 400. 400 amp. Done. So I need a 400 amp disconnect switch. Yes, sir. Because 440.12b says so, and we're not multiplying here. Oh, why did we pick the largest? This is the largest overcome protection device from a system. Feeder over current protection device. The fuse, not the feeder conductor itself. We're coming to the feeder. 440.22b says overcome protection device. Okay. Any question, guys, how we did it? I can't emphasize the word, the confusion all the time happening right here. You multiply both of them by 115. Both of them by 115.
And that, there's 440-12.
B. Yeah. It should be in B. No? Did I give you a wrong article? Yeah, you have to read through the whole deal here. Application rating. What did they say? 440.22. Maybe I gave you the wrong one. Oh, okay. Okay. Not, oh, for that 12B. 12. Okay. B combination. Yeah. Can you see B? B. Yeah. B1A. The full load current equivalent to the horsepower of the two of them. That's a horsepower. No. So the sum of all the current, including resistance, blah blah blah. The combination. Okay, look at B2, full load current equivalent. Do you see that? B2. B2. Let's add 2 here. B2. Right here. So to make it clearer, B2. Can you guys add 2? B2. All right, good point. Let's go to the horsepower equivalent, then we're done. Horsepower equivalent. Now, Chris, since both of them now are going to be interrupted, here's how they do it. The smarter than Chad. Here's how they do it. They add the full load current of the two of them together. They add the full load current of the two of them together. So I have 120 plus 70 equal 190 amp. Okay? And then you're going to go to 430.250. And then they add the lock rotor current too. The lock rotor current, the same thing, 160. Is that the lock rotor current? Right? Plus the 451. So add them up. You end up with 611. 611 amp. So you add the full load current and the lock rotor current, the full load currents together and the lock rotor currents together. Okay? Everybody knows what they did? They just added, because the disconnect is going to interrupt both motors. So it's going to be seeing both full load currents. So 190 and 611. So, and then if you guys go to the table, so let's go, I think it was here. Here you go. So what I need, the first current that I need, we're under 40, so it's going to take us, we're going to go to the lock rotor current. Where is the table of lock rotor current? Here you go. So if you go to this table, guys, back, and I need to size for, the first one is 190. So for 190, go all the way to 190, 190, right? The first one is we add them up, but we need to size. No, this is not the first table. The first table is, oops, go back again, Chad. Yep, right here. I need to size for 190. 190 is 192. Can you guys see that? 192, 190. Cross-reference that baby here. What do you get? 75. So 75. Cool. All right. Put the 75. Everybody can see where we got that one. Add them up from 192 because 190 you're gonna go up 75. So the first horsepower rating is 75. Let's go to the second. Any question about this, guys? The second horsepower rating. Second horsepower rating is from where, Chad? From 251B. What was the amp for the locked rotor current? 611. Okay. Let's go to 611. I go all the way 580. Oops, 611 is right here, right? The next standard. Push that baby all the way, and what do you get? 50. What do you get? 50. Right? Okay. Everybody can see where we got these? One from 251B and the other one from 250. The tables. All right, so we got 50 and we got 75. All right, so let's go back and write them down. So then, this one, guys, will give me, the first one will give me, what did they say, 75? 75 horsepower. This one gave me, from this table, 50 horsepower. And doesn't take a genius to decide that the horsepower rating of this is going to be what? 75, the largest. So the motor is going to be rated for 75. So Chris, when you go buy it, you're going to tell them the following. You're going to tell them that this is a 400 amp disconnect 50 horsepower 240. So 400 amp 240 three-phase rated for 75 horsepower. Any question, guys? Any question? Now, do I need a disconnect for the feeder if I have a disconnect for the equipment? You don't need a disconnect for the feeder. It's either or. And the only time, this is the exception where you size a disconnect to disconnect multiple motors. Not the rule. The rule is every machine, it's on disconnect for safety. Right next to it, with inside.
If let's just say they are connected, you have the one on the feeder, do you not need the one on the other two, or must you have all three?
You must have one in every. Yeah, if you have one in the feeder and they're functionally associated, you don't need one on the branch circuits. But they have to be related to each other, doing some processing. Yes, absolutely. Yeah, because you can't work on the conveyor if one motor is rotating. You're absolutely right. But that's where the functional associated is. But I have an air handling unit here and an air handling unit here, guys. They're completely separate unit. You don't put they're fit from two different separate branch circuits. You don't put a feeder on them disconnect. One for each. Okay, feeder conductor size. That's where my friend Alaribu was upset because he was looking for a conductor size and he couldn't find the conductor size. Conductor size. The conductor size, this is table 310.15 Please correct that one. When we size the conductor size, guys, you're going to do this following piece of cake. 1.25 times the largest, fattest, fluffiest motor. Then you add to it 70, and that will get you, Chris, 220 amp. And then you're going to take it to 310.15 under which column? 75-degree column. And that I don't need to parallel for that. So that will give you 3 conductors. Number 4-aught. A, W, G, T, H, H, N. Done. Why 3 conductors? No neutral. Why 4-aught? Because of the amps that need to carry is 220 under 75. Any question, guys, about this? Any question? Okay, I have two things to do. Should have corrected that one. Okay, any question, guys, about the HVAC equipment? We're done with the HVAC equipment. I need to size one more thing for the HVAC equipment, and I'll get back to that little thing here. Remember that 7A, B, and C? 7 that we added, 7 equipment grounded conductor. Okay, let's do the A. What was the A? The A for the first motor. For the first motor, guys, what was the overcome protection device for the first motor? 110. So for the first motor, so this is M1. A was for M1. M number 1. The overcome protection device was 110. Chris, you take 110 amp to 250.122. I don't have the answer for this. Anybody can give me the answer? 250.122. 110. Number 6. Everybody can see that, guys? Number 6. Number 6. So that'll give me how many conductors? One conductor. Number 6. A, W, G, T, H, H, N, or bear. Okay, this is A. B. B was for M number 2, right? Motor number 2. The full load current for motor number 2. This is, by the way, this is overcurrent protection device here. This is also overcurrent protection device. What was the overcurrent protection device for number 2? 200. Thank you, sir. 200 amp. All right, so let's take the 200 amp. Take them to 250.122. These are cables. Press 200 amp. The same thing, number 6. One conductor. Number 6, A, W, G, T, H, H, N, or bear. Okay, the last one, guys. This is B. Does this look like even B? Here, check. B. C. The last one is C. C. Chris, what was the overcurrent protection device? Feeder. For feeder, overcurrent protection device. What was the feeder overcurrent protection device, guys? We came up with 250, right?
What number was that?
That's the feeder.
Number 4.
Number 4.
Number 4.
Yeah, 250. That was 250 amp. No, it was 270, but we went down to the standard to 250. Yeah, you're right. When we added them 270, but we went down to the actual standard of 250. So for 250, guys, I'm higher than 2, so I have to go to number 4. This is one conductor, number 4. One conductor, number 4. Again, A, W, G, T, H, H, N. Any question about the size of the equipment grounded conductor for each one of these rooftop units or AC units in the wall? Piece of cake, huh? That's it. Let me add one more. So that's basically here, okay? I want to give you the homework in a second. Before I give the homework, this one, guys, if you can go to the first page, the last page, this was left over from example number 1. I apologize. We forgot to do the start current for example number 1. Go all the way, guys, to example number 1. I want to find the starting current for example number 1. Let's go back here. This is 16. Go all the way. There you go. Can you guys see that I gave you code letter? Everybody can see example number 1, code letter number L and M. I gave you these two code letters so you can find the starting current. Cool. Example number 1, L and M. Remember that one. Code letter way at the bottom. So let's go here. Okay, to 16. Find the starting current. Piece of cake. All right. The starting current, guys, from, let's go find it. So I want to remind you that it was L and M. For this one, the starting current was L, and the starting current here was M. Okay, so for this, before I even go start, I have to go to the NEC code book and find the table. We're coming. Oh, the table. The table is 430.7b. 430.7b. So let's go to 430.7b, please, right here. 430.7b. Okay, so for 430.7b, right here, if you guys look at the code letter for the first one is L. Here's my L. L goes all the way to the largest, the upper limit, because that's the worst, 999. The second one is an M, right underneath it, M. M goes into the largest, which is 11.19. I want you guys to read here, says kVA per horsepower with lock rotor current, per horsepower. Okay, everybody knows how to use this. Will give you the inrush current of any motor with the nameplate code letter on it. Which everybody can know that we go to the upper limit because that's the safest, is to oversize it basically. We don't go to the 9.1, we go to 9.99. Everybody got these for the 2 letters? Everyone knows how to use this table. Take a snapshot of that baby. And let's go back to where we were. Okay. Not here, right here. Okay, so here's how we size it. Let's go directly and do the calculation. The first one, remember that 9.99 multiplied by 200 horsepower, right? Multiplied by 1,000, always divided by, the voltage was 1.73 for the 3-phase, and the voltage was 2.8 on that system. If you do the math in this press, you're going to end up with a full load current of 555, 2 amps. Did I do the math right? Can anybody check that? So 555 with 2 amps, if I did the math right. The second one, same way. I start, or inrush, will take the upper limit for this one is 11.19 multiplied by 150 horsepower multiplied by 1,000, divide everything by 1.73 times 208. 208, and if I did the math right, that should be, we did the math right, that should be 664, I want the 4664. Can you guys verify that, please? 4664 amp. These are huge amps, inrush. Now, if your fuse is not rated for this, they'll blow up. It's like a short circuit here. Chris, did I do the math right?
I'm still trying to take some notes here.
Okay.
So, where did you 1,000?
The 1,000, because everything, if you go to the table, it tells you K, in K. Kilovolt amp. So you need to change it into cache the K. The rule is always M the multiplier multiplied by the horsepower times 1,000 divided by the voltage. If it's 3-phase, you have to multiply 1.73. Any question, guys, about this? Any question? Which homework are we on? Homework number 6 now? Number 1, 2, 3, 4. I think homework number 5. Did they give you homework number 6? My record says
We've had 1 through 5.
1 through 5, okay. So homework number 6 and homework number 7. Okay. Any question, guys, before I write the homework for you for number 6 and number 7? I want to use the same example, just change a couple of numbers and make your homework. In a second here. Laribo. Let's go back to, if you guys go to the picture here, because that's the best way to write the homework in here. If you can go right here, and I will change a few things here. The same system, this is going to be homework number 7. Number 6 is coming, don't sweat it too hard. Full load amp. Okay, let's go forward. I'll get back to that one. Here you go. Let's go to this one. This will be homework number 6, guys. Okay, let's use this. Homework number 6. Okay, for these, I want to give you the following. Full load amp, same thing, 2 systems. Let's use a full load amp of, I want to make things make an example that makes sense. Let me take 430 here. Take me 1 second here. 430 full load current. I don't want to give you something that doesn't work. Full load current, 3-phase alternating current. Let's use a nicer voltage this time, guys, for this. Let's use a voltage of 480 voltage, and let's use 480 voltage, and let's use 100 and 125. So let's just 100 full load amp, 100. For the 100, give me a second here. 120. This will be a 120 amp. The second one, I want it to be 150. 150 amp. The second motor. This is a full load current. The horsepower. It's going to be 100 here. 125, the horsepower. Let me just verify that that's right. 100 and up. Yep, right. The voltage for this system is 480 for both. 480 volt. They're all 3-phase. 480 at 3-phase. 480 3-phase. And let's just, oops. Okay. 3-phase. What else are we missing? Code letter. Code letter. Let's say A and B. Code letter A and B. And what else? Temperature rise. Let's say both of them have service factor. Service factor is 1, and the other one is 1.25. Are we missing anything? Is this enough to get you guys to do the whole thing?
Do you have locked rotor count?
That's the code letter, A and B. That's where you get the locked rotor current. Right? So we got the full load amps, we got the horsepower, the voltage, the phase, the temperature, I care less. And I'm just having a locked rotor current and service factor. Any question, guys, about homework number 6? Same calculation, please. Same calculation, these 7 things. Any question? While you guys write, let me write homework number.
Give us something printed with your 7 things that you want.
The 7 things? Okay. 1 through 7. What 1 is and what 2 is? Okay. I can send you an email of that. Any question, guys, about these 7 things that we need, 1 through 7. Can I move to the second one? Okay. So let's go to homework number 7. Okay, homework number 7, guys. I need the full load amp. The full load amp, let's just put this one here. Full load amp. Let me come up with here, right in here. Okay, the full load amp, we size it for, let's size for 233 and 351 amps for full load amps. Locked rotor current. Locked rotor current, usually you multiply this by 6. So let's say this times, say 5. Let's just size this one for 1010. And this size this one for 1200 amp. Locked rotor current. The voltage I would like you guys to use, voltage of the system. Let's use 480 this time for all of them. And oh, by the way, it's 3-phase. Am I missing anything that you need to size the whole system? Am I missing anything? Number 7. And we need to size these 7 things. These 7 things. Any question, guys? Any question? So by doing the AC, guys, Article 440 and Article 430, that's all what you need to size: a chiller, a rooftop unit, a pump. The only thing, the most confusing thing, guys, is when do I use 440 and when do I use 430? You use 440 if your equipment has any type of a compressor in it. Chiller, rooftop units, AC, window air conditioning, anything that has a chiller, a compressor in it. You're going to use your default to 440. Anything that doesn't have a compressor in it and has a motor at the same time, no compressors in it, you're going to default to Article 430. Done. Example: pumps, fans, rooftop units, cooling towers, all fans. We talked about pumps, cooling towers, air handling unit. There's nothing in the air handling unit other than fans. So anything that doesn't have compressor inside that baby. Any question, guys? Between these 2 examples and the homework, guys, you should be able to hit it running and be a designer. So Rob at Michelle Cool Erickson, what they do is, because they don't trust the youngsters like you guys to do, they have a sheet. I don't know if you guys have seen it yet, with all the standard. They say if the overcurrent protection device is this, for this panel, we're going to use this. And you're going to see that their standards might be a little bit higher, not lower, than what we do here. So if the panel need, say 1 watt, you might see them saying 2 watts because of voltage drop. So they lean on the side of safety. What we're doing is bare minimum code. Yes, sir. Homework 7, yep, is the HVAC equipment, the chiller. Any question, guys? That's basically what we do. The only thing I didn't do this time, Nick, is we didn't size the conduit. And now you guys can size the conduit. Take time, size the conduit for it. Not a biggie. From the examples that we do before. Any question? So that's all what we have, guys.